voltage and phase angles of a given power system, buses at all, for all such calculations which are very necessary for the computation of stability aspect viewpoint, security aspect of viewpoint, and the overall balance of active power situation, reactive power situation, and any other planning if so required. For all such purposes, the load flow serves as a basic backbone. In that perspective, we began the study of load flow methods using one of the best method, easier method, Gauss-Seidel in the earlier module. And we could justify it's a simple method, but it is little lengthier as such. And in line with that, how that complex nonlinear equations which get resulted when we connect P, Q, V and delta of a given power system to be solved using numerical solution was witnessed using GS method. There is another method which we call as Newton-Raphson method, which is a very powerful tool to solve such nonlinear equations of mathematical domain as well as for our electrical problem as applied load flow equations which are created are very non-linear in concept. To solve them, we prefer the Newton-Raphson method as well. So today in the class, we will discuss what is that basics related to a Y-bus formation, the nodal form of representation, matrix form of representation of a bus current, and representation of variables. What is that voltage, how it is put in complex notation, what is that admittance of a transmission line, how it is put in complex domain, and how those kind of calculations are put together as a prerequisite to be recorded back before we go into Newton-Raphson method. So in the current slide, you can see the basic equations which we form as a load flow equations are nothing but P and Q calculations. To revise those equations, let us take how that admittance form and current are one-to-one interconnected. The current at any bus is represented by I equal to Y into V, where we can represent the first vector. It is not put in the form of matrix, it is I equal to Y into V. If I expand the variables inside that vector I in the form of column, I'll get several values of I1, I2, I3 like the size of the bus. If I consider n bus system, so n currents are possible at each bus, respectively I1, I2, I3, I4, In. If I put together in the form of a vector, I would see the expanded form or in the matrix form of representation as a column vector containing all the current I1 to In. And the last term, Y into V, V is what? Bus voltage. If you have n buses in the system, voltage at bus 1, bus 2, bus 3, bus 4, the transmission ports where incomer and outgoing terms and load drawal occur. We call them as the terminations where exchange of power takes place. So those bus voltages, if I say n, you will get a column vector V1, V2, V3 and Vn like that. Now what is this dimension matrix? N cross n. It is a system admittance matrix representing transmission mechanism, how they are interconnected to one another. Having n buses in the system, definitely I can connect the transmission element between bus 1 to 2, bus 1 to 3, 1 to 4, 1 to 6, 1 to 7, 10 to 11, 21 to 27, like that. Those many transmission mechanisms, transmission connecting transmission lines possess admittance. Of course, they are impedance. When we want to represent them in the admittance form, I have to take inverse of that impedance represented by that term, and I'll be able to get the net representation of the real-time power system connectivity by admittance notation of that. Then that admittance notation is taken and combined into a representation called as a bus, system admittance bus, where it will possess diagonal elements and off-diagonal elements. So it is what Y11, Y22, so-called YNN represent diagonal elements of the particular system, and other notations Y12, 1N, 21, N1, etc. are off-diagonal elements, which are truly negative of the admittance of that particular connectivity, and the diagonals are some of the admittances of the radiating elements from respective bus to the rest of the buses, which we learned. So this is nothing but just a prerequisite you should recall. Yes, the bus vector I is equal to the admittance matrix of the system into the voltage vector of the system. If I split them, I'll be able to get n independent equations. So bus current I1, I can definitely get I1 equal to Y11 V1 plus Y12 V2 plus Y1n Vn, etc. I can take out one row, nothing but one equation. Second row, second equation. N independent algebraic equation I can take out from this. Hence it's called as a compact form of representation of the system. I equal to Y into V. Then the typical understanding. When I have these information, elemental representation in admittance, how do we represent? We represent them by either in polar or in rectangular. You can just see over here Yij. The double subscript Ij refers to, it is an admittance represented between the buses I and J, having magnitude, the modulus Yij, an angle bracket theta Ij. What it refers? I can just mark the content which I am interacting. This is Yij is equal to magnitude Yij and angle bracket theta Ij, an angle associated with that representation, which if you expand with the trigonometry, you can write, suppose is the magnitude cos of this angle plus J magnitude sin of this. You can see that expanded form. What is this? Yij cos theta Ij plus J Yij sin theta. You call it as a Euler's identity. E raised to j theta. Same expression. So this polar form can be put easily in the form of rectangular, having magnitude and cosine of the angle, and j terms with the magnitude and sine of the theta, whatever we have. This is now called as a real term of the representation and imaginary part of the representation. The non-j is associated with the cosine. That is put as capital Gij. It's called as the conductance part of the admittance Yij. The second term is j associated, which is a complex term, which is imaginary of our understanding, which is Yij sin theta ij represented as susceptance part of the admittance. We call it as susceptance Bij. Now I could see Yij, either it is Yij angle theta ij, or it can be Yij cos theta ij plus j Yij sin theta ij. Or in other terms, in simple notation, it can be in the rectangular form Gij plus j times Bij. The first term refers conductance, the second term refers susceptance part of it. Now, this is with respect to admittance. Now look at the voltage viewpoint. We have several voltages V1 to Vn. How a Vi, a vector of voltage Vi, ith bus voltage Vi can be written. Vi can be written as the polar form magnitude Vi, angle with the delta I. Delta I refers to an angle associated with the vector Vi from its reference. What may be the reference? 0, which the reference stand with respect to the vectorial representation of these voltages. With respect to that reference, it is standing delta Ij away from that reference. So, if I expand this to get the complex representation in rectangular, I could get here Vi cos delta I plus Vij sin delta I. Like Yij, I could get it. Now, it means I should be in a position to understand elemental representation in admittance form and the representation of voltages of the system in the form either in polar or in rectangular. When I know them, when I obtain one of the equation from this compact form of matrix representation, how these are going to be useful to me? Yes, look into the equation. Suppose from the matrix form of representation I1 to In, what I have. Take any possibility I, 1, 2, 3, 4, I, J, K, L, M, N. So, ith possibility in between, the triple dot which is mentioned, extended to In. Somewhere ith bus is there. Ith bus current, I can be taken out as a product of row from the Y bus and a column from voltage vector. If I operate it, what I am going to get? I means it is I current at bus I is equal to Y I1 V1 plus Y I2 V2 plus Y I3 V3 dot so called the last term Y IN Vn. Now you could see here the matrix form. If I expand for a ith bus current, it would look like this, which can be put in the form of compact notation. Summation of n 1 to last number capital N YIN Vn. It means entire string at the RHS side of the capital II can be put as summation n equal to 1 to last bus capital N YIN Vn. Why it is useful? It is useful for me when I want to write similar to the current at bus I, complex power if I want to write. Yes, I require the connected terms. For that, I must recall back what we have understood about the current of a particular bus. If this is understood, if we see how a complex power is explained, the complex power at bus I can be given as SI. SI is what? PI plus JQI. Nothing but it is a part active power and reactive power together SI. How the complex power at any bus is represented mathematically? The bus voltage of that bus, which is VI, and current at that bus, II conjugate. VI conjugate concept is referred, which is V at bus I at bus I, whose conjugate. If I take a product of these two, it will represent me the complex power situation at bus I, which is active power, the first term, real part of that. J associated part is reactive. So it is QI, like that. So which is very important for me. Suppose I want to separate active power, reactive power for my computation point of view. Then how it is done? The usual concept is SI conjugate is taken. When I take a conjugate of complex power, the real term and imaginary term get separated from that. Hence, if I take this equation, PI plus JQI, whose conjugate, it becomes minus JQI, which you can witness over here. Conjugate of the above equation refers to PI minus JQI, which is equal to, on a right hand side, what will happen? Current is having a conjugate, a star mark. Now it will get attributed to voltage and current becomes straight II only. You can see over here. VI conjugate into II, which is nothing but I have taken one conjugate. A size conjugate is taken. Now if I know what is VI conjugate, it's the voltage. A complex voltage of a bus I, let it be as usual, VI conjugate. What is current at bus I? This is the one got substituted from the previous slide. What was the previous slide representation? You can see over here. I equal to summation of n equal to 1 to last bus number YIN Vn in a compact form of single equation of ith bus current, which is being used here. So we can see here in the place of particular VI conjugate, whatever so-called I have here is replaced. Let us see how it is being done. II is equal to summation n equal to 1 to last bus number YIN Vn. Again, we understood how these things are represented in complex form. Suppose you see VI conjugate. What is VI straightforward? Magnitude and angle delta I. Whose conjugate, when I say conjugate, will only affect the J term or angle term only. Therefore, when I have VI conjugate, magnitude will not get affected. You can see here VI magnitude. When I say conjugate of this vector, only either angle or J term will have negative sign. Hence you will see minus delta I. This VI minus delta I is because of conjugate taken on voltage vector VI. If there was no conjugate Vi conjugate like this, only Vi was there, minus delta I would be plus delta I at that time. That is the only change. But here for me, I am taking conjugate of voltage Vi, hence it is Vi magnitude, angle bracket minus delta I. The next term what I have? Summation block with the product Yin. What is Yin for me? Yin is invariably a admittance between bus I and N. I don't know. In polar form, how can I put that Yin? I can put Yin in terms magnitude Yin and angle theta In. I don't know what is I, what is N by its present occurrence. But I can put in the mathematical form Yin in complex notation as magnitude Yin, which you can see over here, and angle associated with that, angle with theta I and N. Product with, what is the vector Vn? Vn is again a voltage of a nth bus. So nth bus will have Vn magnitude, theta N and angle. You can see here. Now theta N, no, is not theta N, it is delta N. Theta is referred to represent angle associated with the element connected to. Deltas are represented as angles associated with the variable voltages. You can see over here. Delta is with respect to I. Delta is with respect to N. Theta is with respect to elemental admittance. This is for the easiness in understanding. So therefore, here there is no conjugate and it is straight away plus representation. Then, similarly, I have the simplified term of which is summation N equal to 1 to last bus number Vi magnitude into Vn magnitude into Yin. Why I did this? Anybody know this? This is a product of complex representations in polar form. We all know the product of complex terms in polar form is quite easier. Take product of magnitude, take sum or differences of the angles associated. Nothing but respect to sign. So in that way, it is Vi into Vn into Yin with their magnitude, a large angle bracket, the angle associated with the particular one, Vi, Vn, Yin should be written here. What is this? Theta In plus delta N minus delta I. You might ask me why you wrote first theta, N later, second, I later. It doesn't matter. It is just a numerical placement, and for easiness we have some trick. Why we wrote I at the last bit? We began with Pi, Qi conjugate, and we are getting. When I separate it, you will have easiness. When I write Pi, delta I at the end of the term is minus. Like that, we have some symmetry of that. We will see that. So theta N plus delta N minus delta I represent the grand angle of which. Now, the next term is, this becomes product of magnitude and this is the angle. Now, as it is in the polar form, if I visualize these three products, Vi, Vn, Yin, as a magnitude of the polar quantity, and all these three angles together, grand angle, some m. So, this is in polar form. Definitely, m cos of that, m sin of that. If I take, I am going to get the real and imaginary part of that. That is being done. Separating real and imaginary part of which. So I take summation N equal to 1 to last bus number Vi, Vn, Yin, cosine of the angle represented inside the angle bracket. Cos of this, if you take, you will see cos in the bracket theta In plus delta N minus delta I. This is standing as active power equation at bus number I. Similarly, if I take the imaginary part of this, what I should operate? The same expression I should expand with the sine term of that angle. I will be having, as there is a minus outside here, you can see here, Pi minus jqi, this minus is outside, this minus comes on other side. Therefore, it becomes minus summation of N equal to 1 to last bus number Vi, Vn, Yin, sine of the theta In plus delta N minus delta I. So these were the equations we have seen once we were interacting load flow study. These two equations are very, very necessary for me in Newton-Raphson method. Why I will tell you. we are supposed to take products of complex numbers. Products of complex numbers in polar form is very comfortable. Hence, this is very easy and these two equations are repeatedly used in solving the load flow requirement. So, once I am able to separate active power, reactive power of a particular bus I refers to any number in the system. If I have 100 buses in the system, I may span 1 to 100. As per the connectivity type, whether bus is a generator bus is a load bus is a slab kind of approach, then according to my type of the bus, number of times I should solve PI, number of times I should solve QI equation is based upon. Therefore, let us say we are able to get PI, QI, the active power and reactive power equations at any bus I in this way. Once if I are able to see, I put again this one, PI, QI, the previous equation. Now what I should do? When the power system is set up with several generators, transmission mechanism and loads, etc. Why we put the power system into existence? To meet the requirement of the end user very effectively, bring balance between active power and reactive power situations so that the end users are satisfied with their requirement. For that, power system corporations should set up sufficient number of generators or any alternative such that the P, reactive power, active power, P and Q, active and reactive power balance must be maintained. In that regard, you can see over here, at the left hand side, I have summation n equal to 1 to last bus number, Vi, Vn, Yin, cosine theta in plus delta n minus delta I equal to active power injected. Nothing but the total demand active power should be equal to active power injected. It should be there. If it is attained, this is called as a steady state of active power. If this equation satisfies the system's requirement, it means this equation is proving you P injected is equal to actual power flowing out. It's called as conservation. Next, will say power invariance, another term. So, similarly, the reactive power equation is equal to reactive power injection. What do we mean by this exactly? The computed power at the LHS side, now I take it as computed active and reactive power. On the RS side, PI and QI, they are called as injected power at the respective buses. They must be in balanced form. If there exists a balance, that equation is perfectly equal, error is less than the acceptable tolerance, system is in steady state. The current generation what you are taken up, meeting the end user's requirement using losses and so forth, all the systems are in steady state like that. If there exists a mismatch, what is the indication? Yes, that's called disturbed state. When P and Q balances are not met, definitely when P is not being balanced, the frequency gets affected. When Q is not getting a balance, voltage profile gets affected. So those two are the indicators to the power system engineer where frequency he is unable to maintain within the range specified. He will come to know that it is because active power mismatch is beyond the tolerant band. When the voltage of the system at particular bus is not able to reach a certain band, scheduled voltage, you are unable to maintain that. It is going out or coming down, oscillating. It is the indicator that reactive power in the system is not met properly. There might be a deficiency or there might be a mismatch, something which is causing Q balance to not to come. Then voltage is the indicator whose the variation or instability indicates that reactive power equation is not balanced. So this way, the power engineer will come to know from the load flow study and steady state analysis of these things whether system is unstable or not stable. If so, what are the other measures one would take is taken care of such things. Therefore, we would see these equations are fundamental load flow equations. Now I am viewing them from the load flow analysis from NRLF, Newton-Raphson load flow technique. Then I'll be using the computed power active, computed power reactive from the basics as injected active power, injected reactive power of any bus I. Now, these are very much useful further. How I'll be using it? Now look into this. When I have two equations, one equation pertaining to active power stability, active power situation, another equation refers to reactive power stability. Now I would like to see how many times P equation I should attempt and solve, how many times Q equation I should keep solving. For this I should understand. Suppose consider a system with 100 buses. 100 buses. I am taking capital N in this system, which is specified you are finding as 100. In that 100 buses, let us consider there are PQ buses and PV buses. What do you mean by PQ and PV buses? There are load buses and generator buses. So which is mentioned N1B load bus. I would say 50B load bus. I am just taking a simple equation. 50B load buses and 50B other generator buses excluding lag bus. Now you listen to me carefully. 100 refers to me now excluding lag bus. Otherwise I would say 101 total, 101 total, one of them is lag bus which is not considered. Only 100 are of my count, 50 of them are load type, 50 of them are generator by type. This may be another way of explanation. Then I would say, look at the capital N. N1 plus N2 plus 1. Therefore, how many unknowns you need to attempt to solve? Look into the load flow perspective. For N bus system, let us forget a slack bus right now. There are N1 PQ buses, N2 PV buses. It means if I come back to the 100 as a situation, 50 load buses, 50 generator buses you have. For these 100 buses, do you know the phase angle of all the 100 buses? Definitely no. When I start load flow study, my hunt is to understand at a load bus PQ are given. V and delta are unknown. I would otherwise say delta at all the 50 buses is not known. Then N1 number of deltas pertaining to load bus I must compute. Similarly, if I have N2 number of PV buses, I would in the example say 50 generators are there, PV is given, P is given, V is given, Q and deltas are not given. I would consider only Q, I mean delta. How many deltas are not known? 50 deltas are not known with respect to generators. Altogether, I would say 50 load buses, 50 generator buses in terms of N1 plus N2. Deltas are not known. I would say 100 deltas are to be computed. That's the first equation. Unknown phase angles delta at all N1 plus N2 pertaining to PQ and PV need to be determined. I would say when I want to work with the Newton-Raphson method, I am trying to conceptualize how many unknown angles are there for me. In a N bus system, excluding slack bus, N deltas are unknown. I don't know 50 generator or a 50 load bus, 75 load bus, 25 generator bus, whatever is the dimension, entire length of dimension, deltas are not known to be computed. That is my statement. So N1 plus N2 deltas you need to determine. The second line you just see. How many voltage magnitudes you need to determine? When I say PV and PQ buses, at PQ buses, definitely V is not given to you. We have to determine voltage of that load bus as well as delta of that load bus. And there are say N1 PQ buses, N1 voltages are unknown to you, surely unknown. What about the PV buses which are N2 in this case, say 50 in this example which I took. Do you know voltage of a generator bus? Yes, you have been given in the problem PV, the name says active power is given, voltage of the particular bus is given. You are not supposed to determine voltage of the particular generator bus. If you do it at the end of the calculation, what you are supposed to do? You are rejecting the magnitude and forcing it by specified voltage of the problem. Am I right? You have learnt it in the Gauss seidel. That would mean from the voltage perspective, you have only N1 voltages not known, which pertaining to load buses. Because N2 number of voltages of PV buses are known to you by the problem itself. Hence, I should say N1 number of unknowns are there from second viewpoint. If I add how many unknowns altogether I will find if I work with the Newton-Raphson method, which is N1 plus N2 plus N1. I will get 2N1 plus N2, or the total number. I don't know delta and V. Total unknowns are me right now are 2N1 plus N2. Now if you apply 50 and 50 now, 50 generator buses, 50 load buses. How many you have now? 100 plus 50 in this case, if I am not wrong. 150 unknowns are there for you. This is a 100 bus system. 150 unknowns you are determining with the 2N1 plus N2 concept. Then we need to write N1 plus N2 real power equation and N1 reactive power equation repeatedly, and we have to solve. Now I am trying to magnify what is the use of PI equation, PQI equation over here. What PI equation refers to? Active power computed. Active power equation connects you to delta. P delta, frequency connectivity. Q and V, voltage connectivity. I am trying to establish the connectivity between unknown and the equations PI, QI. How many times you need to touch that and solve. Touch that, use and solve. I am trying to do. So as you have N1 plus N2 real power equation, PI equation. It's because deltas you have to calculate for all the systems, 100 by count, 50 plus 50 generator and load, etc. All the deltas you have to measure. Delta calculation will go with the first equation. What is that? PI equation, which is with the cosine angle at the LHS side. That equation has to be dealt for those many times N1 plus N2 of the problem. How about voltage unknown? Voltage unknowns are only N2 by your count. It means you have only those values. So therefore, I should say not N2, P2 number of buses. So therefore, there are N1 plus N2 real power specification equation. Only N1 times the reactive power equation has to be touched upon. Why N1 times only? What N1 refers over here? N1 in this page refers to number of PQ buses. Because Q, reactive power equation, if I solve, reactive power equation will connect to the voltage. Voltage is not being maintained appropriately. It is the indicator that reactive power imbalance system. Hence, to address the voltage issue, I must solve reactive power equation. Then, how many unknowns are there for me in the N bus system of a problem? Only load bus voltages are not known. How many load buses I find in this description? Say N1, like a 50 in my statement. Suppose I have N1 load buses, N1 voltages are not known to me. I have to solve them. To solve them, N1 times I should solve QI equation pertaining to bus 7, 10, 12, 50, there's something like that number. So that Q equation I should touch only N1 times. I would connect you all the way to N1 times PI equation I have to solve. Only N1 times I should solve by this equation. So altogether, number of equation I have to handle is determined. This is called as a dimensionizing the problem. Not only this, further when I represent the theory behind Newton-Raphson method, you will come across Jacobian, the partial derivative of the variable derived at initial condition. There again come across a large matrix. We call them as Jacobian. For that also we need to understand the dimensionality of number of PV buses, number of PQ buses in a system. So let us understand. If deltas are unknown to me, how many delta, which equation I must test? If deltas are unknown, PI equation you have to solve. If voltages are unknown to you, QI equation you have to solve. Let us understand this. So I have to touch upon these equations repeatedly. So I connected you from the fundamental to the basic problem periphery. Now I move. Let's see how exactly power flow equation work out. This power flow study need to solve these equations, which I was speaking now. I have to solve that PI, which is a cosine term at the LHS side. What is that? Summation n equal to 1 to last bus in the system, which is capital N, Vi, Vn, Yin, cos theta In plus delta N minus delta I, which is nothing but active power computed at bus I, Pi contact, which is for all I equal to 1 to last bus number and not touching slack bus. So, my friend, slack bus computations are performed only after the convergence of the algorithm. Therefore, wherever I not equal to S, if it is not mentioned also, please remember slack bus voltage and slack bus power calculations are not at all done at the early stage of the load flow. We have defined the slack bus is nothing but mathematical requirement of solution of these non-linear equations. Hence, there is no slack bus in the reality. It is a mathematical preliminary. Okay. Therefore, it should be solved at the end of the convergence. The second equation. What is the second equation? Negative of the summation n equal to 1 to last bus in the system. Vi, Vn, Yin. Wherever I had a cosine, now I'll be using sine. It's very easy to remember. The cyclic flow, cosine when I have it is the active power, you should remember. When I have P equation, cosine comes into appearance. When I have Q equation, reactive power computed at a bus I, sine term appears here for all 1 to n. You can see over there, another condition is put. I equal to 1 to n for all, I not equal to s. Can you see over here? This is a special representation you will not get in textbook. This is represented by one of the authors. I not equal to PV bus. Don't solve this for PV bus like that. We'll see it. When we have a generator and load over there in the same station, I should use. Okay. It is to see that only n1 time you are touching this equation. When out of the 1 to n, out of the 1 to capital N, there are generators, there are load buses. But here author specifically says not equal to slack bus as well as I not equal to generator buses. Otherwise, you would have written for I equal to 1 to last number only for load buses. A single statement. Or this is a mathematical representation. Now, the summary of this can be put as for the unknown variable delta I. How many deltas you have to solve? For all the buses which you find in the system. There are n buses, n angles you have to calculate. Whether it is a generator bus or a load bus, delta is your target. How many deltas? I equal to 1 to n number, not equal to slack bus. 100 if I say 100 deltas. How about the voltage magnitude? Voltage magnitudes of all the load buses only we have to solve, not for the generator. So you are cutting off some work here. So therefore, I 1 to n not equal to s, not equal to PV bus, only for load bus. This is how the gist of the connectivity of active power equation, reactive power equation with the system dimension, which is number of PV bus, number of PQ buses. When I join, this makes me the dimension of the problem. What is that unknown? Delta. How many by number? What is that unknown? Vi. How many by count? I will be able to justify. So this way, this slide enrich me with this understanding. Now, if I move next for a simple example, let's see as example in a 9 bus system. Example, because answer is already there on the screen itself. 9 bus system, bus 1 is said to be flat. How many are left of? 8 buses. Of the 8 bus, look into that. 2, 5, 7 are generators. 2, 5, 7 are PV buses. Least the state variable also indicates a specified power injection. How many power calculations you need to perform? Now look into that. When I have slack bus as bus number 1, 2, 5, 7 as generator buses, what are left of? 3, 4, 6, 8 and 9. If I add them, these 5 those 3 and 1, it become 9 for me. Exactly right. 3, 4, 6, 8, 9 are my load buses in the problem. Of course, I have not been given a single line diagram. I have been given a presentation by text. I will be able to recognize what is the meaning of that. Then, looking to this, you dimensionize the problem. How many deltas are unknown to you in this problem? In this problem, total buses are 9. Leave that flag bus. How many buses are countable? 8 by count. It means you have 8 deltas unknown. Can you see over there? Delta 2, delta 3, 4, 5, 6, 7, 8, 9. All the angles of the voltage vector of buses other than flag bus, you have to calculate. Delta 2 to delta 9, you have to determine. This is the first state variable. Another variable is voltage magnitude. How many voltage magnitudes you need to determine? Look very specifically. 257 are PV buses. What it indicates? Voltages are given at that bus. Among the 8 buses, I will leave the slack bus, 8 buses, 3 are generator by type. Only those buses, 3, 4, 6, 8, 9, haven't been mentioned with the voltage. Can you see over there? V3, V4, V6, V8, V9 are to be computed, are the variable for me. You are able to apply what we learned in the previous slide over here in this slide as my concept of dimension. Then, what are all the calculation you have to perform is nothing but active power injection at respect to buses, reactive power injection at respect to buses. I mean, how do you get this delta and V? I am trying to give you a root. To get delta, I should use P equation. To get V, I should use Q equation. Then how many times P equation I should solve? How many times Q equation I should solve? I am going to give you an indication. To get delta 2, what I should do? P2 you have to solve. P injection at bus 2. Delta 3, P3. Delta 4, P4. You check into that. P2, P3, P4, P5, P6, P7, P8, P9. All those variables, 8 variables you must touch. 8 times. Active power equations you are solving with the proper subscript at the subscript position. P equation has to be touched with 8 times. Then how about the voltages? You have only 5 voltages unknown. To get V3, what I should do? Q3 I should solve. Q4, Q6, Q8, Q9. Can you see over there? Q injection or computed power at bus 3, 4, 5, 4, 6, 8, 9. They are mentioned. So I am very clear. Having this simple dimensionizing understood, you will come to know the massive work involved in power flow solution you can imagine. Imagine 1000 by 1000 bus. Y bus by 1000 cross 1000 dimension. And all these connected things in a computer, just imagine the vast connectivity and dimension of the problem. It cannot be done by human. Hence, computers are inevitable. Earlier, I was speaking, it is the computer techniques in power system analysis earlier. It means, no doubt, power system 2 is the same scope. It calls for need of computer is highly mentioned. So, this is how this problem is just viewed and understanding of the previous P and Q equations with the dimension is witnessed in this problem.